according to the compass rule, the north should be up here. So, but as you see, I didn't write north or south or anything, just because I think that is really up to you. So this is a compass that you can turn however you want. I think I would align it along the line that I've actually drawn, which are my favorite winds. So is northwest, which is Maestrale, and southeast, which is Scirocco, and those are the main winds in our sea. So these are the winds that you use to sail. So in fact, I mean, this line here separates what is more related with quantum information, which you see up here, and what is more related with quantum mechanics, which is here. And I don't know if everyone would agree with this picture, but I think it's quite fair, and at least it helped me to, you know, have an idea of what's going on. I mean, if you have questions about the compass later on, maybe if you look at it, just ask. So the one thing that I realized, speaking with some of you and according also to the questions I found in the box that obviously today I didn't bring because it's the last lesson, so it doesn't make sense. Meaning that you have to ask questions here, now, today, this morning. So what I realized is that perhaps I didn't explain clearly enough where, in what length we are. And as you see on top of the compass, I wrote the compass you need when you are in the open quantum systems length. Now, this is a specific length, so I don't even remember whether I defined what an open quantum system is. But let me repeat it. An open quantum system is a quantum system with an equally quantum environment. And this equally quantum is the key word. So in the literature, there is another word which is used for system whose environment exists, but is treated effectively in a classical way. And this word is closed. So in the literature, you have isolated systems, quantum system without an environment. Then you have closed systems. And closed systems are those having an environment, but with this environment treated not at a quantum level. What does it mean? It means that there's no way your system will develop entanglement with your environment. There's no way you can describe your environment using operators or using this kind of stuff. A typical situation when you have a time-dependent Hamiltonian, never forget that whenever you have a time-dependent Hamiltonian, what you are actually describing is a system which has an environment, and this environment is responsible for the time dependence. And this time dependence is what is left of all the very complicated interaction between your system and the environment. So for instance, when you have a time-dependent field, so you have a spin system in a time-dependent field. What is that time-dependent field? Well, it is something that is a classical description of some quantum magnetic moment interacting with something else, some control system or whatever, that makes it depend on time. Okay? And that is the same, and this is perhaps even more relevant, I realized, with thermal bath. So whenever you have a system at finite temperature, that is a closed system according to the literature, in the sense that is not isolated but is not open, because you do not describe the entanglement generation between your system and the environment itself, the thermal bath. The thermal bath exists, but it is there just to give you the temperature as an external parameter, which is by all means classical. So open quantum systems are the step further, when you don't make any assumption upon the environment, at the point that the environment can have a dimension, a Hilbert space, whose dimension is the same or even smaller than the one of your principal system. So the environment simply means something else, quantum, that interact with your main principal system. And that is why this kind of setting works for measurement apparatuses, many-body systems as environments, but also in all the cases where you have just another system, a qubit with an ancilla. The ancilla or the other qubit is just the environment for the first one. And then you study the entanglement generation, you study back action, and all this kind of stuff. Okay? So that is the reason why the setting is essentially different from that you use when studying isolated or closed system. Is that clear? Yeah. Okay, then the other point is, okay, so but what's the reason why we should use this, this formalism? So why, okay, given that is never a very intelligent, sorry if I'm so rude, but as no senior scientists are around, I can say it. It's never a very clever question, okay? So asking why is some formalism useful? Well, who knows? However, let me just tell you that, for instance, in the 70s, people started to ask, okay, if my system is not isolated and I can't use the second postulate, which is the one saying that, okay, I write it down in the cat version. So this is what I would write in the case of isolated system, and the only condition I have is that this operator must be unitary. So people in the 70s started to ask, okay, so can I have something similar, something that plays the role of this postulate for an open system? Because for an open system, you can't write this, and you can't even imagine each time you have to deal with an open system to get back to the construction I proposed you in the first day. So start from the unitary, trace back, trace the environment, and give all the details. So what are the main features of an evolution which is not for an isolated system, but for an open one? So essentially, what is called the operator sum representation, which is the structure of the quantum process that I described you last time, is the equivalent of this postulate. Is this postulate, people consider it as a postulate for open, for a more general postulate with respect to the one you have for isolated system. And it simply says that whatever the change of your state, it is ruled by something that you can write in this way, where this is linear, this is a super operator. It is a map, a UDM. It has a lot of different names. However, it means that it's linear, it's completely positive, and I will get back to this definition. And it is trace preserving. So these properties are the equivalent of these ones. So for isolated system, you say, I want this to be unitary. For open system, you ask this map to have these properties. Okay? Now, this is what I mentioned in the first lesson, the axiomatic approach to quantum processes. This is the same as UDM, which is the universal dynamical map we've seen, and this is the same as the operator sum representation, which means that you can always write this object in this way. Yes, please.
What is the difference between Krauss and link-plant operators?
Completely other story.
Could you explain the rationale behind it?
Yes. Okay, so at this point, one can ask, okay, I understand the principle, okay? So you've written this, this structure which should substitute this one in the case of open systems. So what? Okay, so one of the first applications of this formalism was actually the derivation of what you probably know as Lindblad equation, but now you find it in the literature more often written as GKSL equation, which stands for Gorini-Kosakowski-Sudarshan-Lindblad equation. The reason being is that these guys here in Poland actually derived the equation before Lindblad. Kosakowski got a very relevant prize just this year for this work. I mean, it was really an exceptional work. So what did they demonstrate? They demonstrate that if a differential equation exists for your system which is local in time, what does it mean? It means that you can write this derivative with respect to time. Sorry, differential equation for the state of your system. Okay. Local in time means that whatever is on the right, if it depends on time, it only depends on the time when you evaluate this object. Okay, so you have no integrals, you have no memory kernels, whatever. That is what local in time means. So they demonstrated that if one such equation exists, then it must have this form. I hope I wrote it okay. I never know whether I put the signs and the two properly, but if there might be, okay, there is a minus here, perhaps 1/2 here, or not? No, because if I write the 2 here, there is no 1/2. Okay, so it should be okay. Where these operators are the so-called Lindblad operator. And this is a completely general result. Okay, and it turned completely. Okay, so remember, this result holds if and only if this equation exists locally in time. This is sometimes what is considered equivalent as saying that you are making a Markovian approximation. Now, again, because Markovianity came several times into the game in these days, remember that it actually does not exist a precise definition of quantum Markovianity. So while you perfectly know what a Markov process is in a classical setting, in quantum mechanics it's not completely clear. And that is the reason why if you look non-Markovianity in the literature, you find a huge amount of papers and a lot of different definitions of non-Markovianity, meaning what is not Markovian. So it is the same as saying that you don't have a good definition of Markovianity itself. Now, this result, if you look in books, is derived in the quantum operation formalism. It wouldn't be possible to derive this result without the quantum operator formalism. So how it is derived? It's simply derived starting from this expression and deriving it in time, okay, if there is time, with some approximation. So what is the relation between the Krauss operator and the Lindblad? No direct relation unless you specify your model. Okay?
So in this case, let's say that we are unable to write.
It only tells you that this is what is called the legitimate equation.
Okay.
But it doesn't tell you anything about what these operators are, and in particular, what they are with respect to these ones. In fact, there's no reason why these operators, the Krauss operators, should be, how to say, directly related with the Lindblad, because in the Lindblad equation, you also have a unitary part here, which is not, you see I've wrote H effective. So this H effective means that this is not necessarily the, how to say, free Hamiltonian of your system. So you can have a part of the interaction between your system and the environment that still give rise to a unitary dynamics, meaning that it does not generate entanglement with the environment. That all goes in here. So the way the Krauss operator, mixed together in order to give this equation is not known. It's not trivial. If you go through the demonstration of this theorem, which is great, you kind of guess how they distribute. But it very much depends on the detail of the models. And that is the way, I know you somehow got confused and perhaps even annoyed by all these different ways I've used to introduce the formalism. But that is essentially the key point. I mean, this formalism needs being introduced in different ways because you use it in completely different frameworks. Okay? So you know nothing about the environment, you use this. You know something about the environment. You can guess for some reason what the Lindblad operators are, then you do this. Or if you know half and half, you can use still another approach. So it very much depends. Do you have a question? Is it clear? Let me tell you another situation where the quantum operation formalism is very interesting, is again for dynamics. So there are situations where you can't use an equation which is local in time, and you have to use and you have to use what is called an integral differential equation. Okay. So this is the most general equation you can write for your state, where this M is called the memory kernel. It is again a super operator, which means that it acts on your operator. It is not just one operator multiplied by. Okay? So it's an action, is a map applied to your operator. And it depends on t minus tau. Okay? Now, one of the typical problems physicists are facing at the moment dealing with open quantum system is, okay, I cannot use this equation because I know that I can't use a Markovian approximation. So I want to use this one. Can I identify families of kernels which are, as they call it, legitimate? What does it mean? You take a kernel, and that doesn't assure you that the final result corresponds to a map with these properties. So when you speak about legitimate kernel or Lindblad operators or whatever, well, in Lindblad is not a problem, it's by definition legitimate. But what it means, okay, I have this equation, I want to find classes, families of kernels such that I'm sure this equation describes a legitimate map. And this is a very relevant problem. Please. This is the most general equation you can write, and this is, in a sense, always true. Okay? Because it's non-local in time. Yes. You can always write from this one, that one, or in general, if you can use the system plus environment approach. That is really very general. But the point is, what is this operator, this super operator? What is this map? What are the properties that this map must have in order to ensure that overall it gives rise, the solutions of that equation are compatible with this? So, the solution of this equation must bring you back to this, and these must obey these conditions.
Okay, so like we have
Yeah, the local part. I mean, most of the time you don't find this, but in general you should put it there. So a local part plus something which has a memory. I mean, I'm not trying to justify the reason for this formalism. I'm just trying to give you some idea about where this kind of formalism can be used. And as you are probably more familiar with many-body physics, symmetries, renormalization group, conformal theories, and this kind of stuff, what is at the moment a very hot topic is, can I use information about symmetries in my environmental model, about properties from the point of view of topological protection or this kind of stuff of my environmental model, in order to find properties both of these operators here or of these ones or whatever. So there's still a lack of connection between what is known in many-body physics as far as, for instance, phase transition are concerned. So it's not completely clear if your environment has a phase transition, what does it happen to the kernel? Or what does it happen to the Lindbladians? Or can I use some information about the symmetry of my environmental model in order to know something about the Krauss operators? All these things have not been developed yet. And they are quite interesting, actually. However, never mind. Let me go on. If you have questions, please do ask. Okay. Another example I want to give you, because it's useful also to understand this compass, is quantum measurements. One of the nicest results that has been recently obtained using quantum operation is that showing that you have an environment that has certain properties, in particular is made by a lot of subsystems, and you make no assumption whatsoever upon that environment, neither regarding the interaction with your principal system nor regarding the interaction between the components of the environment itself. Still, you can demonstrate that the map that you obtain when you let it interact with your principal system is what is called a measure and prepare map. What does it mean? It means that if your environment is big enough and has certain properties, internal properties, which are very general, then its effect on your principal system is that of a measurement apparatus. And this brings us back to the interpretation of quantum mechanics, seeing that the reason why we see the world as it is because, you know, the environment continuously observe quantum systems. I don't want to enter into this, which is extremely interesting and nice. The work is very difficult, but it's amazing. And, this is just to give you an idea of how this general formalism can be used to tackle also fundamental problems. So actually this is the formalism which is at the moment used in studying foundations of quantum mechanics, because it is general enough to allow this kind of analysis. Okay? And that is the reason why perhaps you don't recognize it, but there is a Schrödinger cat here down. Okay? Well, there is a cat. It's not a Schrödinger cat, but it's a cat. Okay. So what we will do today, we will stay somehow along this line for a while, and then you jump north. We will move north, and I will show you how to use this formalism, and in general, this kind of setting in quantum algorithms and quantum information. Okay. Just to get back to your point, actually the problem of finding the relation between the map, the unitary that gives rise to the map, and the Lindbladian is just a very hot topic of research. Okay, so sometimes people think that when they see a Limblad equation, they think that the Limbladians are like S plus, sigma plus or sigma minus, typical Limbladians, have some physical reason to be there. And sometimes people even interpret them as physically doing their job. Like if you have sigma plus, they say, oh yes, there is a reservoir injecting energy or something like that. That is not completely true. Okay?
Objection, then. That's what I want to hear.
Okay. Well, if you go through, my objection is if you go through the derivation of the equation, you see that that is not the case. I mean, these operators here have no direct connection with the interaction between your system and the environment. They come as a mixture of many different aspects, including partial traces. So it's not something that you can really put in direct connection with the interaction. So you see, if you say that the Limbladian follow from some Hamiltonian between the principled system and the environment, that is wrong. That is a wrong statement. And the only way I can convince you about this is just go through the demonstration. It's easy. It's just one page, and you see it immediately. Now, you can make, oh, sorry.
But in principle, what would start from a Hamiltonian which has the system, the environment, the interaction?
Yeah.
Like propagate as you would do, and then trace out the environment, do the Born-Markov, and then you would end up with this.
Yeah.
Do you have an objection with this process?
No.
Ah, okay.
No.
So what is wrong with that?
It's just that these objects here, the Limblad operators, do not directly appear in the interaction. They come in a very complicated way and sometimes have nothing to do with the actual operators entering the environmental system interaction.
Well, we think of the environment having like some oscillators is coupled to the internal system. So like this interaction term is just in the RWA term, sort of A, B, dagger, so like in a sense, we model the environment as okay, a bunch of harmonic oscillators. Is this not should it not be done this way? Or you're saying okay, with some density of states and okay, all the all the complications, but then we have a direct relation between the environment and the system, because the coupling terms involve both. We trace out the ones, we are left with the others.
No, it's just that you have a relation, but it's not a direct relation such that these operators enter the Hamiltonian, the interaction Hamiltonian.
I agree, but
they can be completely different. They can be linear combination. I mean, you already see it because they are not necessarily Hermitian. They are not necessarily terms entitled to enter Hamiltonian.
okay, could you please give an example? Because so far, in what I have seen so far, all these operators, okay, I've only seen A, sigma plus, sigma minus.
Okay.
Could also feature in the Hamiltonian, like of the system.
Yeah.
Could you give an example where one could have an L which comprised of something which does not feature in H effective?
Okay, I can't give it now, but I will give you later, okay? Just to avoid interrupting the lecture, okay? Okay, then, where are we? I always lose my, okay, we are here. Remember to tell me, oh, it's early, okay. Now, I just want to specify, because it is important, what complete positivity means. So when we ask for a map to be completely positive, we mean the following. So given your system, whose Hilbert space will be H, well, let me say H of gamma. Complete positivity means that if you enlarge this system in such a way with an ancillary system, so the Hilbert space of the total system according to the fourth postulate will be this one, then the map, you take any row belonging to this Hilbert space, actually any row belonging to bound operators. Okay? Then complete positivity requires that this map I never know how to deal with the parentheses. Okay, it's positive. Where this is just what is called the unital map. So you always play the same game. You enlarge your system and you guarantee that not only the map is positive upon your density operator, but even if you enlarge the system and you design a map that does nothing to the ancilla, the global map is positive. No, these are, I mean, this is how they usually, this is a symbol used to compose superoperator. It's not an operator, it's a unital map, is this one. It's a map, it's not an identity. Remember that maps are not operators. No, they are not operators. They are superoperators. So they are, you can see it, when you write it here, you understand what I mean, I hope. Okay? So it is not like you take an operator and you apply to your row, as you would do, for instance, with a unitary. So a map is a linear application that goes from one object to another, from one state to another, having the property of being linear and blah, blah, but it's not an operator. It's not an operator, full stop. It's a superoperator. Sorry. No, but it's different. An operator on operator is a thing. A map on operators is a different thing. So what's the difference? Well, essentially the fact that you write it like this if you want.
But still is, operator is not a synonym of map, of function, of everything in the end. And this is...
Well, operator and map is not the same. The operator is something that acts directly on your object. So you only need one. The reason why it's called operator is that you need more than one application to obtain the result, while operator is something that you take it, you apply it, and you get your result. When that is not enough to obtain your result and you need to you know, use more action of what are usually called operator, then you have a super operator. So, for instance, with unitary, when you write this, so Krauss, well, it's the same as written here. Krauss operator is an operator, and this is a map, a super operator. It's like the unitary. So the unitary is an operator, but U, rho, U dagger is a super operator. It's a map.
I think part of the confusion, at least where we come from, comes from the fact that you call it a state. Whereas, I mean, also, this could also be called like a density operator, like in a sense. So in this case, in this could take an operator and map it to another operator, because again, it's like operatorial operator. But if you call it a state, then I suppose this indicates your formalism. Is this at the point?
Maybe, I mean, I guess it is, I hope it's just a matter of terminology. However, definitely density operator are called states. And that, because they are states. And that is the reason why I never used the hat. I don't know if you noticed that I put hat on operators, I don't put hat on the density operator. Okay? So in this formalism, there is a clear distinction between density operators and operators and map.
Yeah, okay, so you make the map much more general and distinct, but I see the point. Yeah. I think for me at least, yeah, it's
yeah, this is the bounded, this is the Hilbert space of the bounded operators acting on this. Sometimes you actually find that rho belongs to this S with the same argument, and S is considered the Hilbert space of the density operators. So it's the Hilbert space of the operators with the unital, with trace equal to unitary, positive, and blah, blah, acting. No, we find out. We have to ask. We require, yeah. Yeah. A plus gamma. Perhaps it is more precise. Yeah, yeah. Questi devo levare perché non sono in ok. In fact, there is quite a lot of discussion about whether complete positivity is necessary or not. It is related with again with the generation of entanglement. So essentially, it says that a map is completely positive if it works as a map, even if your dynamics generates entanglement with something which is not involved in the process itself. So the process is due to the interaction between your system and an environment. Then you think, okay, what if there is another object which is not playing any role in the game? And that condition requires there's no entanglement generation between your principal system and this sort of ancillary further system. Okay, so let me again recap. So this is your process. This is your operation. Map, however you want to call it. This is the operator sum representation. these are Krauss operator. You can also have a different representation which is based on operators which are more directly related with the environment. Do you remember, I mean, the way we first derived this expression? Now, one of the typical use that we make of this formalism is also to reverse the logic. So what you do, you observe your channel, you try to find your Krauss operator according to the process that you study, and then you try to guess from the Krauss operators what kind of interaction with the environment your principal system has. So this is also a very interesting point. Let me end this first part of the lesson, however, giving you two typical examples where we can use this formalism, and actually where this formalism has been used and is used. Okay, so quantum processes for qubits. So now we are moving towards quantum algorithm and quantum information theory. So quantum processes for qubits. Okay. So the first process is what is called state or entanglement transfer. So this kind of processes are crucial when you start playing with qubits. So for instance, if you want to design a processor, but also if you simply want to realize a teleportation protocol, you need to be able to let the quantum state of a system move from one point in the space to another, or from one system to another system, which is what happens, for instance, in teleportation. So you devise a protocol such that if a certain qubit is in a given state, you are sure that after the protocol has ended its working time, another qubit somewhere else in the space is in exactly that same state, even if you know nothing about that state. Okay, this is essentially teleportation. So, for instance, a very typical situation is that where you have a medium, typically for people working in many-body systems, this is a spin chain, and you can use different type of spin chains like XX model, XY model, Heisenberg model. Depending on what kind of model you put in there, you obtain completely different transfer processes. So the idea is that you write and design a Hamiltonian. So here you are at home. So you have something that you know better. So you have this is the case of XX model. So you have a first interaction between your qubit A. Qubit means spin 1/2. Then you have your spin chain. Your spin chain is, a series of spins distributed on a one-dimensional lattice. And you assume that the only interaction between the first qubit and the chain is via the first qubit of the chain itself. Okay, so this is the interaction between the qubit A and the chain. Then you have the chain interaction that, for instance, you can take in the form of nearest neighbor interaction. And then you add something which is similar to this one for the last spin. And you can also add some local fields. Now this is a field, it's not a Hamiltonian or something. This is a very typical setting. I mean, you can change this Hamiltonian here. So these are essentially the control you have on your qubits. You need to be able to apply local field on your qubits here and here. You also typically need to be able to switch on and off the interaction between your qubit and your system. And then you prepare your qubit in a certain state, switch on the interaction, let the chain do its work, and then at a later time, you try to understand what is the state of the qubit B. And you try to understand whether, one, does it exist a time such that after that time, I've obtained a qubit B in a state which is the one I wanted. It could be the same as the initial state of A, or it could be something else. Okay, so, and so first. Second, what are the parameters I have to use in order to obtain this result? So essentially, you need to be able to understand what is the dependence of the whole process on the parameters, external control parameter, J0 and H0, typically. And also, how does the time necessary to obtain my goal scale with the number of spins in the chain? That is very relevant. There are protocols such that this works perfectly, for instance, for state transfer, but it requires a huge time. And that is absolutely not acceptable, because then you want to insert this kind of stuff inside a circuit, inside a processor, where times must be fast, because otherwise you play with decoherence. So you can study this kind of process. A very typical situation that you study in this setting is actually the one where you don't transfer the state of the qubit A, but you transfer the entanglement between A and another qubit A prime. So essentially, you start with a situation where these two are entangled. You prepare them locally. And you want, after a certain time, T star, these objects here to be entangled. This is a very non-trivial problem, because what you want to do is to generate entanglement at a distance. Typically, entanglement is generated just letting systems interact amongst themselves, which means that in a way or another they need to be near. If you have them very distant, for instance, because they are in different points of your processor, and you want to generate entanglement amongst them, you have to resort to some trick of this type. Okay? So again, now I'm not writing all the states, but you can guess that let me write at least something. For instance, in this situation here, the process is a process where you start from a density operator, which is rho AA prime, tensor rho, let's call the chain C CB. So this is the initial state. You have these two qubits are entangled, which means that you can't write the density operator in a separable form. Okay. These objects here, together with the final qubit, you don't care. So maybe you prepare them, but you don't necessarily ask for this to be separable. It may be, but it also may be not. And the kind of process you want to design brings you this into something. So this is the process. Having this structure here. Rho A C prime tensor rho B A prime. And what you ask is that these two guys are equal. This is a typical protocol of entanglement transfer. So at the end of your process, you have that these two objects are entangled in the same way as these two were before the protocol starts. And you can also have, and then I close, with the same kind of settings with spin chains, entangling gates, which means that you play this game here. So you have two qubits here. Now I use a slightly different graphics, but essentially the idea is the same. And in this case, what you do, you start from an initial state which is completely separable, and you move via your quantum process into something where you have this structure here. And this is an entangled state. This is actually quite a nice and interesting class of processes. So again, you can design the interactions and the structure of the chain and of these couplings in such a way that this works, and it works for reasonable times. So remember that although in quantum processes you forget about time because it's just in, out. So I have a goal, I want to obtain this state. I don't put time into my formalism, and yet time is there. So there is a time necessary in order for this object to play the game, and that is actually relevant, in particular, when you look at how it scales with the number of elements of the chain. Let me end this first part of the lesson saying another thing. The way these processes depend on the number of elements of the medium, in this case the chain, but it can be also a more complex medium, is very much related with the symmetry of the medium, with the topological properties of the medium, with the fact that the medium has or has not a quantum phase transition around. For instance, a way to protect entanglement between these two objects, if they are coupled with the chain, is actually driving the chain near a dynamical quantum phase transition according to the, I don't know if you've ever heard the Kibble-Zurek mechanism. No? Okay. However, I mean, all this kind of phenomenology of many-body physics becomes very relevant when you put them inside this kind of problems. Because although at the end you have your effective process which seems to forget about the medium, actually the process is obtained via the medium and the properties of the medium count. Pausa. Dico bene? Pause. Back in. You are the responsible, as we don't have Andrea, you are the one in charge. Well, okay, quarter past, 20 past. Okay? Okay. I need to tell you a couple of things more, and then we move to what I find one of the funniest way of implementing this stuff. The two things I have to explain before, not because they are necessary, but because otherwise you miss a few references in your compass, are the following. Process tomography. And distance measures. So what is process tomography? Process tomography, as you can guess, is the way you can reconstruct your process using the results of measurements. So you have your process, you have your initial state, you have your final state, and what you want to do is you want to do measurements in order to reconstruct the state of your system. So again, see, this is a slightly different perspective with respect to the one you are used to. We are not discussing about measuring observable. We are not discussing about obtaining expectation values of operators. We are discussing about obtaining the structure of something which is not an observable, the state. Okay, the state is not an observable. Okay, the density operator is not related to any observable, it is the state. Please. Well, by process I mean the rho prime. So if you know rho, you obtain rho prime.
Okay, so the final aim would be to reconstruct the state?
It depends. It depends. I mean, you can have state tomography and process tomography. However, I think that actually the distinction between the two is slightly misleading because process tomography is nothing but a tomography of your final state given the initial one. Okay? So after all, process tomography is a state tomography on your final state, given that for some reason you know the initial one. So how does it work? Now, you know that density operator states are elements of the Hilbert space of the bounded operators acting on the Hilbert space of your spin, of your system, which means that you can find an orthonormal basis for density operators. Are you familiar with this? I mean, are you familiar with the fact that you can, define orthonormal bases up on the space of operators? Okay. Inner product, Hilbert-Schmidt product. Familiar with that? Okay, let me write it. I write it. It's the trace of the product. Okay. But I write it down. So So what an orthonormal basis for operator is a set of operators in a number equal to the square of the dimension of the Hilbert space upon which they act, such that orthonormality holds with respect to the inner product, which is the Hilbert-Schmidt product. So the trace of the product, blah, blah, what is defined there. Obviously, here you have an identity. No, it's a trace, so it's a number. Okay? No, not commute. No. They typical example for qubits, you can have orthonormal basis of Hermitian operators, which is the usual identity, and the 3 X, Y, Z polymatrices. So this is a Hermitian orthonormal basis for qubits. You can also use a non-Hermitian basis, which is the one where you use plus and minus. It is fine. I mean, you can easily check that they are orthonormal. Okay. For instance, if you have a couple of qubits, guess it, a reasonable orthonormal basis would be the one you obtain combining all the components. And so on and so forth. If you have a couple of qubits. Okay? So what this means is that whatever the state of your system, you can always write it as a linear combination of elements of one of these bases. So whatever your initial state, you can write it like this. And whatever the final state of your process, you can write it like, let me just change the label, but wouldn't be necessary, obviously. So these are coefficients. I've written here a time dependence that, again, is not necessary, but I don't want to write bj prime, because otherwise it becomes too complicated. So this is essentially the state at the end of your process. Let me write it like this. In the example up there, for instance, is this one. Okay? So the first one is this one, and the second one is this one. You see, formally, you don't even require that the system is the same. As in this case. In this case, the initial system is AA prime, and the final one is BA prime, but that doesn't change your formalism at all. Please.
Notice we're in the Schrödinger picture, right? So where the states are the ones that depend on time, not the operators. So that's assumed throughout.
Yeah. You know that there is this strange situation with density operator.
Yes.
Because they are states and they are operator, and that's the reason why in the Liouville equation you have a minus sign. Okay. Okay, so if you use this orthonormality condition, you can easily check that these coefficients here, which are essentially what you need in order to understand your process. Okay, so tomography of the process means basically to derive these coefficients here. Once you have them, you know how to go from here to here. And if you want, you can find your Krauss operators or your dynamical elements or whatever. Okay? So you use the orthonormality condition, and you find that these are nothing but the trace over the trace of the final state times the element you're interested in. That's trivial. I mean, you just happy? Is that okay? Okay. Now, this is the expectation value of this operator by definition as obtained while making measurements on the final state. That's very simple, and it's the key of process tomography. Now, at this level, it's not enough yet, because you still don't know exactly how to deal with this. So what you actually do, you start preparing your system in elements of the basis rather than in linear combination of them. And you run your process. So essentially what you do, let's say we are in that setting we saw before, the simplest one. So you start with the state of your qubit A prime. These are entangled, and you want this. This is rho prime, which is A prime B. So what you do, you prepare this qubit in one of these states. So you set here only one coefficient different from 0. You let the process go, and you take measurements of this object here, and you obtain a number. And then you change this, and you do it for all the elements of your basis, and you obtain what is called the dynamical matrix, which is essentially this object here. The trace. So essentially the dynamical matrix element, let's say Ij, is the coefficient Bj at time t given the initial state zeta I. So you construct all these elements, and with all these elements you get your final state, and you can play the game and obtain the Krauss operators and so on and so forth. It is a transfer matrix. It is essentially, the first time I saw it, I didn't know anything about this, but I had worked with transfer matrix. I thought, oh, but that is a transfer matrix. It's a transfer matrix without all the passages through the chain, where you have I plus 1, and so on. It's called dynamical matrix. It can be much more difficult. The message I want to send you is that one of the reasons why measurements are so relevant in this setting is that at the end, in order to study these things, you need to make measurements. I mean, this process, and you need to make very precise measurements. I mean, this is not any measurement, because this object here is an element of the orthonormal basis. Now, with qubits, it may sound trivial, because, as I said, these elements are identity possible elements, sigma x, sigma y, sigma z. So it means you are actually measuring the components of the spin along x, y, z direction. But in other situations, you can have different bases, and you can need to make different kind of measurements. So you see, we've started from a very general formalism, and we end up to measurements, which is very physical, actually. Happy about it? Do you have questions? Okay. Obviously, at the end, if, for instance, you wanted, here is where distance measurements comes into play. If, at the end, you want to know how good your process was with respect to some goal that you had put yourself. So I want rho prime to be this. Like in this case, I want rho prime A prime B to be equal to initial rho between A and A prime. So you have to find a way to measure how different processes are. And here you have two kind of fundamental measures. One goes under the name of fidelity. Fidelity is nothing but the, apart from a factor of 2, if I'm not wrong, the trace distance between your states. So fidelity between two states is just which is there are several different ways of defining these objects. However, you have two states, two density operators, and you want to understand how different they are. You use these measures. This is the fidelity. I'm not going into the details. It simply comes from the theory of operators. So that is a proper legitimate distance. It has all the properties a distance must have in the space of operators. Okay? There is another one which is very recent and very nice that works for maps. Because sometimes you don't have the state and you only have your quantum operation. So you need to be able to define the distance between two different maps, say E and T. So in order to evaluate how different two maps are, you use what is called the Diamund Norm. The Diamund Norm has been recently introduced, and it is defined in this way. You, again, need to enlarge your system allora. So again, what you need to do, you need to enlarge your system, define this map here, which is the map that does nothing to the ancilla and acts on your system according to the map you are studying. The dimension of the Hilbert space of the ancilla, it is demonstrated that if this holds, then this distance does not depend on the details of the ancilla. So essentially, this is a way to evaluate how different two processes are, not considering their action on a state. You see the difference between this measure and this measure. So this requires you to have two states and ask yourself what is the difference between the two states. This one is more general and tells you, I don't care about the input state. I just know that this sort of device gives me a map. And I want to see how different this map is from the one I wanted. Please.
So the maximum with respect to what?
All the possible states, because you have state here.
Okay, so we still take the trace to result to be like this.
Yes.
Okay, so in the end,
But I mean, the tricky point is that you really have to maximize over not all the density operator, and it is not even enough to do it for your system. I mean, you could in principle think, oh, that's okay. It is not. So unless you enlarge the system in this way, you don't have a proper measure. Because the point is whether this is a measure or not, whether this is a legitimate norm with all the properties of norms. Okay. There is another definition of the Diamund Norm due to Kitaev, which is slightly more easy to understand, but it is much less used because what matters with this kind of distance is to find bounds. I mean, no one really tries to find this maximum. It would be a nightmare. You can't even know where to start from unless you are in very simple situations. So what you actually look is bounds for these distances. So if you can demonstrate, for instance, that this object is always less than or equal than something, then you're happy. And the Kitaev definition doesn't allow you to find these bounds as easily as this definition. So this is the most used in the literature in recent years. Okay? For instance, when I, at the beginning of the lesson, mentioned this idea that you can demonstrate that the environment acts on the system as if it were a measurement apparatus, so the Copenhagen, if you want, interpretation of quantum mechanics, is actually demonstrated using this distance. So what they demonstrate is that if one of these is the map corresponding to a measurement process, and the other one arises from an environment with certain properties, then that distance goes to zero. So you really play with these distances in order to understand how similar quantum processes are. Is that clear? Good. Okay, and now we don't have a lot of time. I will try to be as fast as possible. Now we head north. We really jump towards the north of our compass, and we see how can we use some of the things I've been telling you in these 6 hours to have fun. Well, at least, if you find it funny. Okay, so there exist problems which are called combinatorial problem. And there exist problems which are called combinatorial optimization problems. What they are, I try to be as fast as possible because we don't have enough time, but I give you an example. Typical example, we were discussing with Laura before because it's called max cut problem, but actually I have always studied the min cut problem. How it goes that you have a graph which is not directed. What does it mean? It means that the lines that connect your vertices do not have a direction. Okay? So you have a number of vertex and you have a certain number of connection and whatever. I think it is not in principle necessary that it's fully connected. I mean, you can start with whatever. And this kind of graph, usually you represent it with this notation. You see V stands for vertex, E stands for edge, and usually you label it in this way. You give names to vertex, and edges are just named after the couple of names of the vertices they join. Okay, so you have a vertex U, a vertex V, and UV is the edge that connects the two. So the max cut problem is a problem that asks you, is there a way to divide this graph into 2 subsets, which means to group the vertices into 2 subsets, in such a way that the number of edges which are cut by this partition is either maximum or minimum. Okay? So usually it's called max cut, which means that you look for the maximal number of cuts. The way I've always studied is the minimum, but that doesn't change much. The problem is it possible to divide this graph into two subsets? Well, put it this way. Is it possible to divide the vertices of this graph into two subsets in such a way that the number of edges which are cut by this division is either maximum or minimum? So essentially, you do a cut, and then you count how many edges did I cut in order to do this partition, and then I try either to maximize or to minimize the number of cuts. Okay? This is a very typical problem that needs being solved in dealing with traffic jams, in studying social networks, in studying a lot of problems. If you want to know more about this category of problems, there is this amazing paper. I really like it. It's Andrew Lucas, and it is Frontiers in Physics. Tooth. A bunch of zeros. How many are they? 4 and 5. Where he essentially lists a lot of problems of this category, and the reason why he chooses these problems is that these are the problems that can be mapped into Ising models. So what is the point? The point is, I have this problem. Can I formulate the problem in terms of some cost function, which is the cost of the cutting of the edges in this case, in such a way that this cost function actually is a Hamiltonian for a model. And then I find the ground state of the Hamiltonian. So that's the logic. Let me see it in slightly more detail. At the moment, we are classical, okay? Completely classical. So I use this example as a guide. The kind of construction I'm going to make can be used and reproposed for other problems, other models, and so on. So what you do, you associate to each of these vertex a binary variable, plus or minus 1. Okay? An Ising variable, as they call it, although it's classical. And then you write a function which has this form: A sum U belonging to the set of the vertices of, okay, so SU is the variable that you associate to the vertex U, and then plus B sum over all the edges. Now, what you put here is a cost function for cutting an edge. How do you make it? Well, essentially you say, oh, sorry, I forgot to tell you one thing. Sorry about it. Okay, so forget. So how do you characterize whether a vertex belongs to one subset or the other? Okay, by this variable. Okay, so I forgot to tell you. You want to divide the set of vertices into two subsets. So how do you say whether a vertex belongs to one or the other? You say, well, if S of u is equal to 1, it belongs to subset 1. If S of u is equal to -1, it belongs to subset 2. Okay? So given this, you can define a cost function for the cut of an edge in this way. You see that if u and v belong to the same subset, this is positive and equal to 1, and this object amounts to 0. So if the edge connects vertices belonging to the same subset, this is equal to 0. It doesn't cost anything. If they belong to different sets, which means that the edge is cut, then this is positive and equal to 1. Okay? Is that clear? So this is the cost function for cutting edges. And this is the cost function for having an unbalanced couple of subsets. So essentially what this tells you is that you need, remember that this can be plus or minus, and you want to divide the set of all your vertices into two subsets of the same size, which means that these, if you obtain your goal, this must be equal to 0. Okay? So this is the cost function for unbalanced, say, subsets. And this is the cost function for cutting edges. Okay? So essentially, what you want to do is to minimize this object over all possible combination of the variables, of the binary variables. Okay? It's not necessarily fully connected, as I said. So the connection, it depends on the graph. You are given a graph and you want to solve the problem. Fully connected means that each vertex is connected to all the other vertices in the graph. So that is not a condition, necessary condition for the problem to be formulated.
So if you really think to be adjacent,
No, I mean, it doesn't matter whether they are adjacent. I mean, they must be connected by, yeah, I mean, that is this condition here. I mean, sorry, the notation is a little bit contract. This notation means that UV must be an edge. Sorry. When you define a graph in this way, this is the set of vertices, this is a set of edges, of links. And so when you write this, it means that UV must be a link.
A simple one link, like not like.
No, so in graph theory, edges are connection between vertices, direct connections. Okay. Okay. Now, these are the family of problems that you can somehow represent by, sorry, you see that this is an Ising model, okay, classical one, okay? Remember that whenever you have a squared of one of this is just a trivial constant, so from here you have couplings, you also have couplings here, so it's an Ising model. Pardon? It's not because this is not a fully connected graph. So there is a part which is mean field, which is this one, but there is a part which is not mean field because it depends on the graph. Okay? And so the idea, okay, these are very famous problems that has been studied in classical computation. They've been classified as far as their complexity is concerned. And recently there have been several ideas suggesting that if you embed this kind of problems into a quantum Ising model, so simply you promote these classical variables to quantum operators for spin 1/2, so this becomes sigma, then it may be that you find an algorithm or a device such that you can solve this problem, which are usually very, very hard to be solved on classical computers, on a quantum device in a much faster way. This is not demonstrated. It's just an idea. It is also very much discussed whether the effort you need to put in order to devise the quantum device, to design, sorry, and realize the quantum device to implement this kind of calculations is so big as an effort, then it doesn't make any sense to think about it. But still, it's very, I find it very, well, I find it fun just to try to map these problems into some quantum problems, but that depends on your choices. However, now, it's not the end of the problem. The point now is that we have another tool in our toolbox, which is the Adiabatic Theorem. So if you agree with me that our problem is reduced to finding the ground state of this Hamiltonian, then you can think about the Adiabatic theorem that tells you that if you have a system with a time-dependent Hamiltonian that is very slowly varied, and in this time-dependent Hamiltonian you have two terms, a main one and sort of, well, not secondary one, but I'm now using a notation that if I have time I will use it later. I don't think I have. No, non mi piace scriverlo così, scusate. Fatemelo scrivere per bene. So you have a Hamiltonian, which is the sum of two terms that do not commute. And you are able to tune these two functions in such a way that it exists a time, capital T, which is known as annealing time. Such that, so you are able to control these couplings in such a way that these relations hold. What does it mean? It means you start your process and you only have this term here, and you end your process and you only have this time here. Now, this term here. Now, this term is going to be the Hamiltonian upon which you have mapped your problem, and this term is actually the one that you choose in order to design the initial state of your system. So essentially what you do, you design the initial state of your system, of your algorithm, of your register in an eigenstate of this Hamiltonian, and then you play with these parameters, and using the Adiabatic theorem that tells you that if you are clever enough and slow enough, you can actually remain in the ground state of this overall Hamiltonian for the whole time. At the end of the annealing time, you actually end up in the ground state of your Hamiltonian, which is the solution of your problem.
Just to clarify the notation, the Hamiltonian, the argument is always, right? Or is it increasing
No, it's t, it's t. So this is always t, while this is capital T, which is the end of your process and is the annealing time. Now the chairman is suggesting that my time is finished, so I'm sorry I can't go into the details of this idea, which is actually very nice. However, to make it short, the idea is that this Hamiltonian defines a propagator where you have two terms that do not commute. So you can't write the propagator, so the propagator is just the time ordering of e to I minus I integral okay? So what you do at this point, you discretize this integral. You use Baker-Hausdorff-Campbell formula in order to separate these two terms, throwing away terms deriving from the commutator. And you end up with something which is perfectly described by an algorithm having this form. I want to show you the algorithm at the end. And you repeat this same block as many times as necessary. So here is your initial state. These are the states of your qubits, your spins. Plus means 0 plus 1 over 2. And this is because we choose, for instance, for this term here, something which is local, and for instance, it can be sum over I sigma Ix. This for sure does not commute with this one, because you see this one has sigma z as operators. And so essentially you divide your protocol into steps. This is where you apply h of gamma, and this is where you apply h of beta, and each step corresponds to a different time interval in the discretization of this integral. I don't pretend you to understand everything because I'm very...
So what do you make h of gamma in your first one?
Yeah. Because h gamma is non-local. Is actually, as he suggested, is mean field. I mean, there are a lot of interactions. So h gamma acts on all your input, while h beta, you can decide to use it local. It's not necessary, but it's easier if you take it local. Okay, so remember that h beta doesn't appear in your problem, in your original problem. It's an auxiliary Hamiltonian that does not commute with the original one that you use in order to rule the adiabatic process. And
What's very slow in this process?
what is very slow? Well, in this case, you forget about slow and you just think about how many times you have to repeat this scheme. And what is relevant is the total time, and that is because that, again, you have to compare with decoherence time and the time of the running. At the end of the story, you end up with something. Sì, ho finito. So you repeat this, you end up with a state, which is the state of the whole overall system, rho prime, let's call it, and you make measurements up on them. And you obtain information about the ground the state, the final state. The final state, if everything worked nicely, is the ground state of your original Hamiltonian, which is the solution of your problem. I'm sorry I was a little bit fast in this last part, but I hope you got at least an idea. Okay? Thank you.